Today, we're diving into some really cool research that's all about teaching software how to find its own flaws. And trust me, this is a huge deal because it could make our entire digital world a whole lot safer. I mean, it's a question we've all asked, right? You're right in the middle of something important, and then, bam, your favorite app just crashes. Or you wake up and hear about yet another massive data breach. It almost always comes down to these tiny, hidden mistakes buried deep in the code. And those little mistakes, well, they have a name: software vulnerabilities. The best way to think of them is like tiny cracks in a digital wall. Most of the time, they don't do anything. But if the right person finds one, they can cause a ton of damage. So the real challenge isn't fixing them, it's finding them in the first place. Which brings us right to the bug hunter's dilemma. How in the world do you even start looking for these invisible flaws? You have to understand, this scale of modern software is just staggering. We're talking millions upon millions of lines of code. Trying to find one specific little bug by hand, it's pretty much impossible. It's a truly astronomical challenge. So naturally, we built automated tools to help us out. And one of the most promising ones is called directed fuzzing. It's a fantastic idea, but as we're about to see, it has one heck of a flaw. Now, to get what directed fuzzing is, just look at this comparison. The old school method, that's coverage-guided fuzzing. It just kind of pokes at a program randomly all over the place, hoping it trips over a bug. Super inefficient. Directed fuzzing, on the other hand, is way smarter. It identifies a specific, suspicious area of the code and focuses all of its energy right there. It's like knowing exactly which section of the library your book is in. So, what's the problem? Sounds great, right? Well, the researchers behind this paper kind of hit the nail on the head. Even though these tools know where to look, they have no idea how to look. That fancy phrase, input mutation strategies, that's just the way the tool changes the data it's feeding the program to try and trigger the bug. And the problem is, they're just making random changes. And this gets us to the absolute core of the problem. This deep, deep inefficiency of using a random approach for a very specific, targeted job. So here's the paradox, the real head-scratcher. We have this super smart tool that can pinpoint a target with incredible accuracy, and then it just starts throwing random stuff at it, hoping for a lucky shot. It's a colossal waste of time and computing power. And this is not a small issue. The research shows that over 65% of the attempts, the mutations, made by these fuzzers don't even get them any closer to their target. Think about that. The majority of the effort is completely wasted. This illustrates the difference perfectly. The old method is like an archer firing thousands of arrows into the woods, just hoping one hits the target. But this new approach, the one we're about to get into, is like having a single guided arrow that you know is going to hit the bullseye. So how do we make that leap from firing blindly to hitting the bullseye every single time? Well, the answer comes in the form of a new tool called IDFUZZ, and it is designed to be that intelligent guide. Honestly, the simplest way to think about it is this. IDFUZZ gives the automated bug hunter a brain. It completely replaces the random guesswork with actual learning and experience. Okay, so what is it exactly? IDFUZZ is basically an add-on, a module that you can plug into the fuzzers that already exist. It uses a neural network, that's the brain we're talking about, to analyze every single test it runs. It learns from all of them to make the very next test that much smarter and more effective. So, how does this brain actually work its magic? Well, it all comes down to learning from experience, but with a really clever twist. And this right here is the key insight. This is the brilliant part. See, most systems are designed to only learn from their successes, but IDFUZZ learns just as much, if not more, from its failures. By comparing what worked with what didn't work, it can start to figure out which specific parts of the input data, what the paper calls the critical fields, are the ones that actually make a difference to the program. The whole process becomes this really elegant loop. So, step 1, the fuzzer generates some test inputs. Step 2, the neural network, the brain, analyzes the outcome. Did it get closer to the target? Farther away. And then, step 3, it uses that knowledge, that new experience, to intelligently guide the creation of the next test. It literally gets smarter with every single cycle. Okay, so that all sounds fantastic in theory, but does it actually work in the real world? Let's take a look at the data, because these results are, well, they're genuinely impressive. Just take a look at this chart. It shows the time it takes to find a vulnerability. The bars for the standard fuzzers are pretty high, but the bars for those exact same fuzzers with IDFUZZ plugged in, the difference is just dramatic. On average, IDFUZZ makes these already state-of-the-art directed fuzzers more than 2.48 times faster at actually finding bugs. That's not a small jump. That is a massive leap in efficiency. And hey, remember all those wasted attempts we talked about earlier? The ones that didn't even get closer to the target? IDFUZZ reduces those by almost 92%. It basically stops the fuzzer from wasting its time on changes that just don't matter. And this isn't just a theoretical exercise. Using this exact method, the researchers found 6 brand new, previously unknown vulnerabilities in software that is widely used and has been tested for years. That means 6 real-world security holes are now patched and secured, all thanks to this smarter approach. And what might be the most impressive part of all of this? It achieves these incredible results with only a tiny 6% performance overhead. It is the absolute definition of working smarter, not harder. You know, this whole thing leaves us with a really fascinating final thought. This technology is about so much more than just finding software bugs. It's a powerful demonstration of how we can build systems that intelligently learn from both their successes and their failures. So the big question is, where else could we apply this powerful idea?